So let's continue the discussion on Jen junction. Okay, this is what we started last week. And as I told you, we are going to derive three important equations for the Jen junction, right? So this is the first one. That's the contact potential between the junction band for the Jen junction, right? So maybe I can tell you the equation before we start to derive it. This is the first one, which is the contact potential given by this equation determined by the concentration of doping, right? And remember, this is under the assumption that we assume all of the electrons and the holes are fully activated from the impurity levels, right? So this is what we assume in the red box. So if the ionization percentage is not 100%, we need to slightly modify the final results by the percentage of activation, right? For example, if you only have 90% of the electrons and holes excited from the impurity level, we need to multiply the Na and Nd by 90% because that's the doping concentration. Okay? And this is actually the potential difference sky, right? For the Jen junction. Right? So when you are deriving some equations, always remember the assumption, right? This is where the difference comes from when you compare the results with the theoretical equation and the experimental measurements, right? There's always a difference. Usually that's the one of the origins or the causes leading to the difference between the theoretical calculation and the real measurements, right? So you need to go back to review the assumption to see if this assumption is the real case, right? So that's one of the ways you can evaluate the accuracy of your measurements. And that's the second equation we are deriving today is the width of the diffusion region. Right? That's the region where we have the internal electrical fields. Due to what? Due to the space charge, right? You know space charge. We talked about this last week, right? So this is the region where you have the ionized donor acceptors without electrons and holes. So we call this diffusion region where we have a P and N. And in the P region, if all of the acceptors are ionized, they will become negatively charged, right? Because they lose the holes, which is positively charged, right? So this is negative charge. Negative charge on the P side, and the positive charge on the N side, right? So we call this space charge. What do we mean by space charge? Space charge is the charge fixed in the certain space, not movable, right? Because the charge is from ions, not from electron holes. Okay? And I hope you still remember the only 4 charges that you can find in the Jen junction. What are the 4 charges? Anybody can tell me, remember? 4 charges, 2 of them are positive, 2 of them are negative, right? And the 2 of them are movable, 2 of them are not movable, right? You remember the 4?
Is NA the ND?
Yes. Na negative, ND positive, right? NA is the acceptor for the donor, no, acceptor for the host, right? And the ND is the donor concentration for the N-type, right? These are the two charge not movable, which is the reason for this space charge. Right? And out of this space charge, we call it the neutral region, which means we have equal numbers of positive and negative charges. So the sum of them is 0, right? So it is called the neutral region. Right, so we know this width with space charge is very important for two kinds of devices, right? Because this region is the active region that can produce usable currents for the solar cell and the photodetector, right? Because for the solar cell and the photodetector, they are producing electrical currents by photons, right? So when the photon is exciting the electrons in the valence band, if the energy is high enough, sufficient to excite the electrons from the valence band to the conduction band, only the electrons excited in the depletion region can produce usable currents. Right? You can also excite the electrons in the neutral region, like in the P region or in the N region, right? Excitation can happen anywhere as long as the photon energy is larger than the band gap, right? This is the band gap. But these electrons and these electrons are useless. Why? Because they are not moving anywhere due to the lack of electrical fields, right? So we call this useless photoelectrons. Photoelectrons. Okay? This is also useless. You mean useless, right? Useless means although they are free, but they are not moving to the direction you like. Only the electrons excited within the depletion region, within the space charge, usable. Why? Because they can move to the same direction due to the electrical fields. They can move to the same direction due to the electrical fields created by this space charge, right? So I'm just to tell you, if you can make this region wider, you can produce higher photocurrents, which will give you higher quantum efficiency, higher conversion efficiency of a solar cell, right? So you can produce more currents with the same number of photons. So solar cells and a photodetector, if you are making this kind of device, solar cell, converting the optical energy into the electrical energy, if that's the device you are trying to make, one of the key design for you to design the device is to make this depletion region, make a W as large as possible, so you can produce more currents under the same photon energy, right? So how do you evaluate this width? it is also determined by the doping concentration. Give me the answer before we derive it, right? Equation can be very long, right? Right, that's all you need to calculate the width of a PN junction. And C is also determined by the doping concentration, by the temperature, by the material you choose, right? Ni is the intrinsic concentration, which is determined by the material type, like the silicon, gallium nitride, and arsen, right? And then this is coming from the potential voltage, right? So our next step is to derive this long equation, okay? So as I told you last week, whenever you are deriving the equation, you need to make the right choice for the starting equation. What is the starting equation for this guy, okay? What is the starting equation for this guy? There's a reason we do this first, because the width of the depression region is related to contact potential, right? We need to find the electrical fields inside the depression region. Because you know the electrical fields is related to the potential drop by the width, right? If the electrical fields inside this depression region is a constant, right? The simplest scenario is this is electrical fields. If it is a constant, and then you know the potential equals to the electrical fields times the distance of their distribution, right? So you can know the fields, electrical fields, the magnitude of the electrical fields, and then you know the total area, which is equal to the contact potential. You know this, and then you know this, you can determine the width of this depression region, right? So our next step for the width of the depression region is to find this guy. What is the electrical fields inside the depletion region. Okay, what is the depletion of electrical fields inside the depletion region? Okay, we start from the simple equation. Do you think if the electrical field is a constant or variable, change or not change is the distance? If you want to make a guess, number one is a constant, number two is not a constant. Which one you would choose? How do you determine whether the electrical field is constant or not? You can look at this figure and know the right choice. So, what did you say? 陈冠佑 constant or not constant? Constant or what? Because it's simple, right? 因为什么？啊？电压差。我是问什么？我说那个电场是固定的，还是一直变化的？会随着位置变化，还是跟位置没有关系？它就是一个常数。You know you have a different locations within the depletion region, right? So there must be electrical fields, right? So these electrical fields will change with position or not change with position. 你说不会，对不对？有什么原因吗？直觉。直觉就没有原因啦，我就是觉得它要是 constant 的 ，right？ 同学，你同意吗 ？constant or not？ 你也同意 ？For any reason？ Now， 我们问一个更直觉的问题啊。I make this question more intuitive. Okay? Imagine if you are an electron. Imagine you are an electron. Okay? Okay, two electrons, okay? One electron is sitting here. Okay? One electron is sitting here, which is in the center of the depletion region. One is in the edge or the interface or the boundary of the depletion region. Which electron will experience the more electrical fields, will be pushed stronger by the electrical fields. You know electrical fields is in this direction, right? This is the direction of electrical fields because you have a positive charge here, negative charge here, right? If you are an electron sitting here and sitting where, which position will be pushed more? Will experience stronger electrical fields? Center or edge? According to your answer, you said doesn't matter whether you are sitting here or here. You feel the same electrical fields, no change. Is that what you say? 要修正吗？啊？啊？不用修正，都一样，对不对 ？OK。不一样，为什么？你改变心意了。我知道位置不一样了。对，我要问，为什么位置不一样，电场就不一样？想想看，电场怎么出来的？一个简单的理由就是同性相斥，异性相吸嘛，对不对？ Electrical field is from Coulombic Coulombic force, which is 库伦力. It will push away the same charge. Will attract each other if we are in the opposite charge or different charge, right? 所以你觉得不一样 Any special reason making you change your mind? Hmm? 想问出来吗？对啊，So you can imagine, for the electron sitting here, it will be attracted by this positive charge, which is on the right hand side, right? So this electron is being attracted to the left hand side because there is nothing here, there is no space charge here, right? This electron only feel the pull force 吸过去 right from the left hand side because there is no charge here, only charge here, right? And for this electron, it's been pushed from the left hand side because they are of the same charge, and then it's been pulled by the positive charge. One side is pushed, one side is pulled, right? So in other words, this electron is feeling pull force in the same direction. On the left hand side, the electrical field is push electron to the right hand side, to the other side. And for the space charge here, it's been pull the electron toward the same side, right? So the real answer is that electrical field is at the maximum values, right at the boundary between P and it will reach the maximum here, and it will go almost to the zero at this boundary, right? So this is the actual distribution of the electrical fields. I can show you. See? This is the electrical fields as a function of position, right? It is in the negative direction, so it is negative, right? Because negative is defined from the right hand side to the left hand side. So this is defined as the negative position, right? So you can see it is at the 0 point between the diffusion region and the neutral region. It gradually increases to the maximum. Why? Because at the boundary here, you have a one side pushing you away, the other side pull you toward it, right? So this is the position where you feel where the electron or holes feel the maximum electrical fields right at the boundary of the p-n junction. And these electric fields will go smaller gradually as it is leaving the boundary between P and N. Okay? Do you agree? Okay, so it's another constant part, right? So this is slope. So this is making our question more difficult. It is not a simple multiplication of the constant electrical fields and the width of the region, right? It is actually a triangle. You need to do the triangle area. You need to calculate the area of the triangle, not a rectangle, which is easier. But this is not too difficult, right? You know the equation for the triangle area, right? So you just need to know the height and the width of the triangle, right? So our next step is to know what is the maximum, which is the height of this triangle. 对，三角形的面积 长乘以比乘以高除以2，简单，对不对？我们只要知道它的高就好，高就是 electrical field maximum amplitude, maximum electrical fields, right? So what do you need? You need Poisson equation. Because Poisson equation can tell you the slope of this triangle, which is the change of electrical field as a function of x, which is the position. Right? So according to the Poisson equation, you know how to determine the electrical fields, how to determine the slope of the electrical fields. It is determined by the charge density, right? Which is making sense, right? Because charge is the source of Coulombic force. Coulombic force, you know it? Coulomb, right? Coulombic force is the force from the charge. Whether you have a positive charge or negative charge, Coulombic force will attract the charge with different sign, right? Positive will attract the negative charge, and the negative or positive will push, repel from each other, right? So this is the source of electrical field due to the force of a Coulombic charge, right? So Poisson equation is to tell you if you have a more space charge, you're supposed to feel stronger electrical fields or stronger change of electrical fields because you have a more source producing Coulombic force， 对不对？空间上面的电荷如果越多，它产生的电场就越强，这个合理，对不对？因为库仑力就是同性相斥，异性相吸，对不对 ？OK， so in order to know the slope of our electrical fields, we know the starting point of the electrical fields is 0 because out of the depletion region there is no space charge. We call it the neutral region. So no space charge, which means 0 electrical fields. That's why we don't have any lines outside of the depletion region. So electrical fields. Comes 0 here in the neutral region, 0 here in the neutral region, right? So we know the starting points of your electrical fields is 0. Next step, if you can know the doping concentration, you can know the maximum by doing the slope, right? So the next step is to understand the second figures, which is showing you the charge density as a function of position, right? Charge density, one side is negative, the other side is positive, right? So that's the distribution we plot for the p-n junction. And in this figure, we intentionally making the doping concentration not the same, which means one side is of higher doping, the other side is of lower doping. In this example, you can see we have a more N-type doping than P-type doping. So we don't have an equal distance of the space charge. One is wider, one is narrow, right? So my question is, what is the total charge for the N side, which is Q plus, right? This is Q plus. Q plus on the N side. And Q minus on the P side. Because they are not of the same concentration. So I'm just asking you this equation. If your donor concentration is larger than acceptor. This is for N type. This is for P type. What is the relationship between Q plus and the negative? Q plus and Q minus. Again, you have two choices. One is equal to each other, or not equal to each other. Which one you would choose? 一样还是不一样？两边都有空间电荷哦，只是一边是正电，一边是负电，对不对？我要问大家，全部加起来总正电荷跟全部加起来总负电荷一样还是不一样？二选一。Q plus is the total positive charge on the N side. Q negative is the total charge on the P side. Are they the same? Not. 吴彦霖，你觉得呢？一样还是不一样？为什么？直觉嘛。Please give me a reason. 什么叫电中性？它们中间没有电中性啊，中间是一边是正的，一边是负的啊，对不对？电中性只有在外面非空法区的地方才是非正空。Neutral region is only happening outside the diffusion region, right? What do you mean by 电中性？其实有一点讲对了，可是不够清楚，对不对 ？You think about where is this space charge from？ 空间电荷是怎么来的？为什么那个地方会有正电荷？因为什么不见了？啊？怎么不见？对啊，电子不见才会有正电荷啊，对不对？电子如果没有不见，就是中心区的状态嘛。中心区的状态就是电子的负电荷去抵消 donor 的正电荷。Right? This is what happening in the neutral region where you have a equal number of negative charge and the positive charge, right? So the equal number of a negative charge is from electrons. And the number of a positive charge inside the neutral region is from the ionized donor. When they are of the same number, they cancel each other, resulting in zero net charge. But this is not what happening inside the diffusion region because you have almost zero electrons. Where does the electron go? Well, 中间空法区的电子跑去哪里 ？Where do the electron go? Why do they disappear? 怎样？为什么不见了？中间的电子为什么不见了？2个礼拜前，你有来吗？那你应该还记得吧？电子为什么不见了 ？Why does electron disappear? What do they do? Where do they go?
结合。
跟谁结合？
电导。
Yes. The electron disappear because they go to recombine with holes, right? So there is no electrons left and no holes left inside the diffusion region. And that's the very reason for you have the net charge inside the diffusion region because you have no electrons, you have no holes, right? 电子如果是一颗的话，它要跟几颗电动结合？一个嘛，对不对？一个电子只能跟一个电动结合啊，不可以劈腿啊，对不对？一个就是一个。In other words, if you lose one electron due to recombination, at the same time, you lose another hole because of the recombination event, right? Because one recombination event will simultaneously reduce one electron and one hole because they are recombined with each other, which is a one-to-one connection, right? One-to-one behavior. So up to now, you should know the reason, right? 如果这样子的话，到底是要一样还是不一样？
一样。
一样啊。Of course, it is equal to each other, right? Because you are losing the same number of electrons and the same number of holes because it's a one-to-one recombination, not 1-2, not 1-3. One loss of electron is producing one loss of holes. So they are lost at the same time. If you have a lost 100 electron for the recombination, simultaneously you lost another 100 holes due to the same behavior of recombination, right? So this is due to the loss of electrons, due to the loss of holes. So as a result, they should be the same, right? Due to the loss of electron, due to the loss of holes. You can also say due to the recombination, right? Which is the loss. This is very important because this relationship will give you a very important conclusion. You know Q plus equal to what? Q plus Q A X N 0 N D and the Q minus Q A X P 0 N A. One is negative, one is positive, but I'm looking for the absolute value, just the absolute value, not the sign, right? So if you make this the same, because you know Q plus equal Q minus, you can have Q A X N 0 N D Q A X P 0 N A. Right, what is X N 0 and the X P 0? You look at the figure. Xn0 is the position corresponding to the boundary between the depletion region and the neutral region on the N side, right? So that's the boundary on the N side. And the P0, XP0 is the boundary on the P side, right? So these two numbers, Xn0 and XP0, is telling you the width of the depletion region on the two sides, on the P sides and N sides, which is very important because it is inversely proportional to the doping concentration. What do you mean by inversely proportional? You can understand from this equation, right? Because A is the cross-sectional area, right? I hope you know it. Cross-sectional area. Alright, so you can cancel the same terms. And finally, you will see this important equation. Xn 0 times Nd equal xp0. What does this green box telling you? This green box is telling you if you have a higher doping concentration, you will have a shorter depletion region. Or if you have a very low doping concentration, you will have a very long depletion region. Okay? That's the important conclusion. Due to this simple equation. Right? This is an important concept, producing important results. Why this is important? Do you know why this is important? As I mentioned, if you are designing a solar cell, or you are designing the photodiodes, photodetector, which is to convert optical energy into electrical energy, you need to make this region, make the depletion region as long as possible, so you can receive more photons and producing more useful electrical currents, right? How to make this long? How to make the W larger? According to this green box, you should make the doping concentration low, not too heavy, right? Because if you make this large, this will become small in order to produce the same product for the other side, right? Because the multiplication of concentration, doping concentration, and the depletion width supposed to be a constant, which means one is large, the other one must be small. If you want to make X large, the best way to do it is to make a doping small, right? So you pay attention to the doping concentration of a solar cell and the photodetector. You will see inside the active region, inside the depletion region, usually they want to make the doping concentration very low in order to increase the depletion region. Okay? But you cannot make it too low. What will be the problem if the doping is too low? If you make the P and N too small, what is the issues? Something bad will happen if you make the doping too low. Although you can receive more, you can deliver, you can generate more photocurrents, more photoelectrons, but something bad will happen, you know. What is the something bad? You know?
Previously is very small.
Say again?
Is the reason is disappear in the thing so long.
No.
Because the positive negative in solution.
No, if you make the division up, you make the doping concentration low, you will make the division region longer. And what happened? There will be an issue. You think about the very motivation for doping. Why do you want to dope the semiconductor? What's the reason you do doping? Yeah, to make it more like a conductor, right? Because I mentioned P-type is supposed to connect to the anode, 正极, N-type is supposed to connect to the cathode, 负极, right? Because anode is producing a lot of holes, cathode is producing a lot of electrons. You need the holes and electrons flow through the p-n junction and go back to the other terminal, right? So if you can make the semiconductor more conductive, you can reduce the resistance, right? Doping is to reduce the resistance. You can save more energy, right? So if you make the doping too low, you will increase the resistance, which will take more energy, which is not good, right? If we are considering the power saving, you are considering the power consumption, you want to save as much power as possible, you should increase the doping for the device, because higher doping will give you lower resistance. However, if you want to produce more photo currents from the sunlight, from the optical energy, you should reduce the doping concentration in order to make the diffusion region wider. Right? So there's a trade-off. Right? You got to make it low in order to increase the diffusion region, but it cannot be too low, otherwise you will make the device like a resistance. Right? So there is a balance. Considering the power consumption and the efficiency, conversion efficiency, right? 效率跟耗电跟省电有时候是互相要牵制，对不对？好 ，right? So this is an important some important conclusion you need to keep in mind, right? This is used. This will be necessary when you are deriving this equation. Okay? So that's the three important figures you need to keep in mind, right? The space charge distribution, the electrical field distribution. So you can see if your doping concentration is a fixed value, a constant, you will have a constant slope here, which will make your calculation easy because it is basically calculating the area of this triangle. If your doping concentration is not a constant, which means the slope is not a constant, then the math will become very headache. Math is not easy. You need to do integration, right? 知道哈？ If I am so bad， 假设我心肠很坏，考试给你考一个doping是一个 x 的函数，那你这个面积就很难算啊，它不是比乘以高除以2而已啊，因为你的三角形的边长是一个渐进式的曲线，就不是一条直线。Okay，because the slope of this triangle or the slope of electrical fields is determined by the doping. So if the doping is a constant, the slope is a constant. If the doping is not a constant, slope is not a constant, which will make the calculation ugly, right? Because it's not a simple calculation for the triangle area. You need to do integration little by little. Okay, so now I'm telling you the starting equation. Starting equation for the diffusion region width. If you know this, you do the integration. You know the results of the integration, which is the potential drop between P and N. You should know the width of the diffusion region. Right? The rest of the steps are simply algebra. 就简单的代数而已，只要你会积分 ，OK？ Okay, so this is what we talk for the diffusion region width. So I hope you can know more about the Poisson equation. You will hear it very often if you study solid-state physics. Poisson equation. Okay, whenever you heard Poisson equation, it is to tell you how to calculate the electrical fields with lowering charge density. Okay, let's take a break. 电脑。